My name is Ebenezer Chinyati. I'm going to be showing a demonstration of my master's thesis titled Securing IoT Devices Using Hyperledger Fabric, a Blockchain Technology. The setup is two hosts, a Kali Linux AMD64 architecture and a Raspberry Pi ARM64 architecture. So on this window, we have the Kali Linux. I'm going to show the kernel OS. By running unum -a, we get to see that it's running Kali AMD64, the 2020 July version. So on this device, it is supported by Hyperledger Fabric. AMD64 architecture is supported by Hyperledger Fabric, and the images are readily available through their documentation. Through execution of a single script, it downloads the Fabric samples, the binaries, and the images as well. So those have already been set up. When we run Docker images, we get to see the list of images available from Hyperledger Fabric. These are the images available. And I'm just going to show you the folder structure of the project, Fabric samples, which is also downloaded from Hyperledger Fabric. However, for this project, I have cloned this folder, and I've also put the project folder IoT project inside of it. The folder has to be the same for Kali Linux and also for Raspberry Pi, because their configuration files, the core YAML, which has all configurations for the peers and all other components for Hyperledger Fabric, as well as the ODERA file, which has configurations for the ODERA file. So when this is downloaded, the Fabric samples folder is downloaded on a machine, there would be need to also download the Fabric samples folder for this project and then paste it into the same folder so that the components needed for this project are available. After saying that, I'm going to show you that currently there are no containers running except the Prometheus one, which is already dead. So we'll remove it by running docker remove, and then it's removed. Containers run on top of Docker images, and the Prometheus container, as I'll show later on, is the one used for the metrics. When we run docker service ls, we also see there are no services currently running on this machine. Now, to go to the Raspberry Pi machine. The Raspberry Pi machine is running Raspbian OS. When we run unum -a, we get to see that it's Arch64, and it's a Linux version as well, a Debian variation. So, on this machine, Hyperledger does not provide images for ARM64. To build images for this architecture, and the build process would require downloading of source code. The source code, after it has been downloaded, Hyperledger Fabric source code, it needs to be put in the Go path. So I have my Go path here with the source folder under GitHub Hyperledger. I have the Fabric CA, Fabric, and Fabric base image. Within these folders, there's need to edit the Docker files. The Docker files are the configuration files used for creation of images. So inside, let's say for CouchDB, there is a Docker file that needs to be edited. Take, for example, this one. So the Docker file needs to be edited, and new values that are specific for the Debian operating system need to be put in. The Debian operating system that is ARM64, like for this instance, ARM64. After editing of these files, we then run make docker within this folder. But I'm not going to show the process because it takes over 2 to 3 hours. However, after building of these images, there was a need to upload them to my Docker Hub repository. So I'm going to show that. This is my Docker Hub repository of all the images from the time they were built: base image, Zookeeper, base OS, CA, and all. The ODERA has recently been built, as you can see, it's 4 days ago. When you open in there, each image is a different tag. So some tags are way older than others, depending on which tag is being pulled at that particular time. As you can see, this one is even a month older. From that position, I created a Hyperledger downloading script to download these files. This script can be found within the IoT project under scripts. It's called download Hyperledger Fabric images. So on this machine, the images have already been downloaded. When the images are downloaded, they are downloaded straight from my Docker repository, and then they are retagged to Hyperledger Fabric orderer. The retagging is to allow them to look the same as the ones we have on Kali Linux. However, in this example, I'm going to remove one of the images, the smaller image. So I'll remove the orderer image and re-download it again. So it's being used by other repositories, the ones that have been retagged. So I'm going to force its removal. Now it has been removed. So I go into the folder that has the script and run the download script. So it will download all images that are being called within that script. However, if the images are already there, it will only check their validity. This is the script. With some of the images commented out, the CouchDB and CA, because they're not being used in this illustration, but they've already been developed as well. So we'll give it a minute or two. Now it's downloading the Fabric orderer. As you can see from here, the tag which I was using when I was, after creation of the images, I was tagging them as ARM64 so that they are specific tags. And the ARM64 is the version number, 0.4.20 is the version number of the image that I was creating. So now the images have been properly downloaded. If I run Docker images, we would see that these are now the images there. So I'll go back on the Kali Linux and I'll clear the output and run Docker images again. For this instance, let's take the peer 2.1. We copy that and we say Docker inspect. We want to inspect the peer image. And we scroll up, we want to see the architecture. As you can see, the architecture here is AMD64. We come here, we look for the peer 2.1 as well with the same tag. And we say Docker inspect and then the peer number. Keep writing this wrong. We scroll up again looking for the architecture. We also get to see that the architecture there is ARM64. So that's the difference that is there. The images were successfully built on the ARM64 architecture, which is one of the biggest contributions of this project, because there were no instructions and no documentation on how to deploy Hyperledger Fabric on an IoT device or an ARM64 architecture device. With the images downloaded, the next thing is to set up Docker Swarm, which will be used for the multi-host configuration. So when we run docker node ls, it will show us that Docker Swarm has already been set. We have the two devices, the Kali Linux and the Raspberry Pi, already communicating with each other. The same output is given there. And when we run docker network ls, we get to see that the IoT network running on overlay driver is also already set up. Both devices can see this network. This is the network that is going to be used for setup of the containers. So if we come here and go inside of Docker folder and we open for host 2, the YAML file, I want to show you where the network is specified. The network is specified here as an external network. That's the IoT network. So now we will bring up the host. For Kali Linux, it's host 1. So we run host 1 up. And then on Raspberry Pi, it's host 2. So we run host 2 up. So the Kali Linux has already downloaded the containers. If we run docker ps -a, we get to see that the containers are up. Then we'll also do it on Raspberry Pi. Now, containers have also been set up on the Raspberry Pi. We get to see that these are the containers where we have orderer2, peer1.org. Here we have peer0.org, orderer, and orderer5. This multi-host illustration is running using Raft ordering service. So there is a minimum of 3 orderers. If one of the orderer falls, the other takes charge to become the main orderer, the leader orderer. So after running this, the next process is now to create the channel. So I have a script as well for the creation of the channel. This script is found within the IoT project within the Fabric samples. So if we open the script, we get to see that these are the instructions that are there. It creates I'm going to comment this out so that it does it properly. It creates the script using the channel artifacts that have already been created, and then it joins the peer, and then it also joins peer1.org.example, which is the peer on the Raspberry Pi. So we run that script, create channel.sh. As you can see on the output here, it has been successfully submitted and the channel has been updated. To check, we run docker exec peer channel get info -c Ebenezer, which is the channel name, and that is the height that we now have. Run the same on the Kali Linux to make sure that we have the channel also set up there. And we also see that the height is the same and also the hash is the same. After this, the next step now is to install Prometheus. So Prometheus will be used for measuring of the metrics. We use this script, metrics Prometheus. It will start Docker server and create a container using the Prometheus.yaml file. This Prometheus.yaml file will scrape for metrics and check on peer 1, Odara, Odara 2, and peer 0. So Odara 2 is on Kali, Odara 2 is on Raspberry Pi, peer 1 is on Raspberry Pi. It will also be getting metrics from that device since they are both running on Docker Swarm. So when we run the metrics Prometheus, the Prometheus server will start and we'll be able to access it using our web browser. Now, when we run docker ps -a, you will see that the Prometheus container is just started 7 seconds ago. These are the other containers we had running. And if we go on our browser and we type localhost 9090, the Prometheus server will start. So this is the Prometheus server. It has now begun executing. If we go on status and on targets, we see that all our targets are currently up. If any of the targets falls, we'll be able to also be notified from here. When you go on our graph, for now, I want to show you the height, the ledger height, since we have already checked and seen that our blockchain height currently is 2. When we execute this, we get to see that the value is 2 all across. So when it improves, we'll be able to see this. That's what the Prometheus server does. Back to the system. Now, we go on our Raspberry Pi, and we now want to execute the chain code. To execute the chain code, we open deploy chaincode.sh. Chaincode had to be deployed on the Raspberry Pi due to inconsistencies that were there with the architecture, and having the images being built for this project couldn't figure out a way to have the chain code being executed on Kali straight into the Raspberry Pi. Sometimes it executes, but it also fails when it's now trying to commit the chain code due to the inconsistencies that are there. And also sometimes it fails when it's just trying to build the images across due to also the inconsistencies. So we'll start by copying the access.chaincode.tar file. I'll go on a new tab and we paste this. So what it's going to do right now is going to copy this file into our command line interface. We press enter. Oh, sorry. cd fabric samples IoT project ls. Here is the file. So here is the file we want to copy into our command line interface. Enter. So if we say docker exec CLI ls, we then get to see that the access chain code file has now been copied into it. There it is. So now to install it on the Raspberry Pi, we run this command. It will take a little bit of time, and I'm also going to copy the command for installing it onto the Kali Linux. So for installing onto the Kali Linux, there is need for definition of the Kali Linux peer address, where the TLS server is, because this needs to be a confidential communication. So these files are specified in the script that I will be executing for installation into the Kali Linux. So for now, we'll wait for a minute so that it installs the chain code on the Raspberry Pi. So the Chaincode is now installed. It took a little bit of time, but now it's installed on the Raspberry Pi. So we'll now install it onto the Kali Linux. So as I was explaining earlier, the core peer address gives us the peer address and the port number for the peer on the Kali Linux, which is peer0.org.1, which we find here, and the port number, which is 7051, which we find there. And then it will direct us to the core peer TLS file, which will also be found in the Kali Linux, but as well as on the Raspberry Pi, because they do have the same files. So after installation, we get to see an access package identifier created here. It will be needed for the approval of the Chaincode. So we copy the instructions for approval of the Chaincode, including the access identifier I was just talking about, and the Chaincode will now be approved. After approving of the Chaincode, we then check the commit readiness. This is to check whether the Chaincode is now ready to be committed. So the membership service provider for organization 1 will approve, and it will give us this output to say, yes, it's now ready to be committed. The next step is now to commit the Chaincode. Committing of the Chaincode will create containers on both the Raspberry Pi and on the Kali Linux. So on the commission, we need to have init required, because that's part of the functions which we have inside of our Chaincode. Now, when we run docker ps-a, we get to see that the container has been created for peer 1. If we run the same on the Kali Linux, we also get to see what? The container has been created. Now we go onto our Prometheus server, we refresh, we see that our ledger blockchain height has changed. It was 2 for some time, and then it moved to 3, and then now it's 2 to 4. The changes which are there is when we committed the Chaincode, and also when we installed the Chaincode, we're adding new blockchain heights. We're adding a new element, a new asset inside of our blockchain. Hence the change, and it's showing that our blockchain is working correctly. So back to the other tab, we have now just committed the Chaincode. The next step is now to query the Chaincode. So when we query the Chaincode now, we're trying to see the Chaincode definition itself to see whether it has been installed and committed and approved correctly. And also our approval is still to true. After querying the Chaincode, now we've come to the step, the interesting step, which is the invocation of the Chaincode. So the invocation of the Chaincode includes creation of the first value being put into our Chaincode. So the first value is going to be Ebenezer Chinyati with the isInit flag. So when we press enter, the Chaincode has been invoked successfully. We come on our Prometheus and check again, the block is still 4. So we come back here on our Raspberry Pi. After querying it, we now want to invoke the Chaincode. The invocation is to see, that's the value which we had before. We now want to invoke the Chaincode to get a new value. So now we are going to set a new value. The value which we had was Ebenezer Chinyati, but now want to set a new value. Enter. It allows us to set a new value, which is Prel. That will also change the blockchain height. Now it has moved to 5. So how do we then get to see the values that are within the blockchain on the Kali Linux, you ask? Which will give us the value Prel, which is the value we just invoked. So if we do the same on the Raspberry Pi, we should also get the same value, which will be Prel. That's it. So now we also want to set a new value on the Kali Linux to show that the blockchain is being operated across both devices. And we say paste. We change this to Tracy Kandea. Enter. So the container is down. That's why it's failing. We come here, we check the containers. We see that our containers have exited. These are some of the challenges which we have when we are running this system. So we would need to bring back up the containers and rerun the script. They're now back up. So the script was invoking the orderer file and also checking the PS0 and trying to set a new value. So we execute it again. And now we see that Chaincode has been invoked successfully and the value is Tracy-Kandea. We come here and we try to check the value. We get to see now that the value is Tracy-Kandea, showing that the invocation was successful. So the explanation which I gave earlier of why we have to run these instructions for this project or the instructions for Chaincode on the Raspberry Pi is what we've just witnessed, where it could fail and also the container could go down when you run it on Kali Linux due to the differences that are there on the architecture. I couldn't go into the depth of trying to fix the kernel issues due to the limited time of this project, but the Chaincode invoked successfully. If we go on our Prometheus and check, we get to see that our blockchain is now 7 from the Tracy-Kandea and the prayer which was added. Now, to conclude on the Chaincode, the purpose of this project was to have access control measures being set by the Chaincode. So now we will try to get the value using a user account. This user account is user1@org.example.msp. If we click enter, it will give us the value. So a user, a general user, be it they're using web UI or they're using command line, they would need to use their particular username and the cryptographic materials which they have. Either using a REST API so that they don't get to show the location of where the files are, but they'll be using their user account to be able to access values on the blockchain. Be it temperature sensor, be it weather, be it a camera feed, they would need to use their account. However, when that same user now tries to set a value within the blockchain, it should fail. Because a user should not have the rights to set the values. They do not have the access to be able to do that. So when we do that and press enter, using that same user, which is user1, we get to see only admin can set new value. Only admin can set new value. Checking again on the blockchain height, we still see that our blockchain height is still 7. To conclude the video recording, now it's 11 hours since the first containers were created on both Kali Linux and on Raspberry Pi. As we can see here, the containers have been up for 11 hours and no new data has been added other than the test which we had before. If we go on our Prometheus, we can see the state is still up. So to finally conclude it, we're also going to check the block height again to see what the current blockchain height is. We execute it and we can see that our blockchain height is still 7. Would need to move it like this for us to see from the last time we committed something. We last committed at 10:14 and up to now, 12 hours, 11 hours later, the block height is still up to 7. Something to note, there is another channel, BMHN, sys channel running below. This BMHN was created on generation of channel artifacts. That's why it's down here below. It only contains the channel definition and the Genesis block. Channel Ebenezer is the one we can see here. As you can read, hopefully, the channel name is Ebenezer. That's the one which has the height 7. So this is the conclusion of my project. I've illustrated how to run Hyperledger Fabric on AMD64, ARM64, creating a channel that is being run on top of Docker Swarm, deploying Chaincode, and also demonstrating access control using Chaincode. Prometheus time series was used as the metric benchmark tool, and after 11 hours or 12 hours, I've also demonstrated that the blockchain network is still running, the Docker Swarm is still active. Despite the network challenges, everything is working normally. Thank you.